podcast is brought to you by LMU Munich.
Because they're the three questions that I hope will be answered. Now, of course, these questions will be answered, but these are three questions that I hope will be answered in my lifetime, which is a non-trivial constraint. And I think we should keep them in mind in the larger perspective on this grand journey of string theory. The first question really has to do with what motivated many of us 30 years ago to return or to take string theory seriously, and it is, how do the forces of nature unify? And here I'm extremely optimistic for a variety of reasons. One of them is that this is the question on which we're most likely to get direct and invaluable experimental guidance. And this year, in that sense, has been an extremely exciting year. And we heard a wonderful talk from the convener of the Higgs analysis group in the ATLAS collaboration about the recent ATLAS CMS discovery of the Higgs particle. Now, some of my friends here have told me that they're very disappointed that the Higgs particle, or what seems to be and surely is the Higgs boson, was discovered. It would have been much better if it hadn't been discovered and we would be perplexed and challenged. That really would have given us stimulus to find the right direction. I think that really is totally wrong. This grand exploration that we've been embarked in now for decades to try to understand the unification of the forces is only conceivably possible because it rests on the firm foundations of the Standard Model, which has now, received one of its important, perhaps final confirmation. The Higgs boson discovered indeed agrees extremely well with the Standard Model. If you look at the plots of the branching ratios of various channels and the total cross-sections observed so far, these look like high-precision tests of the Standard Model. The Standard Model works. Is that bad for exploratory physics? Is that bad for our quest to understand the unification of the forces? No, it's great. At the press conference that was held here on Tuesday, the reporters kept asking, can string theory be tested? And is it really science if it can't be falsified? And Juan Maldacena made a very good point that I'd like to reiterate, and that is that in the Popperian sense, string theory every year is being put to the test. For the last 30 years, the experimenters could have discovered phenomena which would contradict and threaten this whole approach to the unification of the forces in the way that we imagine within string theory. There are two sides to the Popperian point of view. One can falsify a theory by discovering phenomena that don't fit naturally into the framework, and one can, even better, if one has a real theory that's predictive and allows one to make quantitative predictions, falsify it by quantitative disagreement with observation. Well, we're not at the second stage of being able to subject the postdictions or predictions of string theory to quantitative falsification, but we have been, for the last 30 years, in the situation of being conceivably making discoveries that would threaten this whole approach. And that hasn't happened, and we should take comfort and inspiration from that, including this verification recently of this important new sector of the Standard Model, where we might find indications of new physics, but in any case, it enormously strengthens the foundation of our attempt to go beyond the Standard Model. And we know that there is physics beyond the Standard Model. We know that because of experiment, the existence of dark matter, a particle presumably discovered by astrophysicists. It's not in the Standard Model. Neutrino masses, baryon asymmetry, cosmic acceleration. None of that is within the Standard Model. We know for good theoretical phenomenological reasons that there must be physics beyond the Standard Model. So I would say that the experimental situation continues to be, and in fact has improved dramatically. And we continue to have reasons to believe that there is physics at the TV scale, that some of these questions are addressable at the TV scale, including, of course, the electroweak scale. And so we might see evidence for supersymmetry, to explain the hierarchy, explain unification. And unification itself has not been threatened by observation and experiment over the years. The fact that the forces of the Standard Model fit together so beautifully in SO10 or many other unifications remains correct. It has not been threatened for the last 30 years from the extrapolation of the Standard Model to a Planck scale. And this could have happened at any time during the last 30 years. It remains correct. It remains true that so far there has been no threat. So far, string theory, or the attempt to unify all the forces of nature at the order of the Planck scale, including gravity, which led to the great revival of string theory 3 decades ago, remains unthreatened. That, in other words, string theory for the last 30 years has not, and it could easily have been falsified. Also, the hope that at the TV scale supersymmetry is an essential component of string theory, could be seen, low energy supersymmetry. The clues for that remain viable, and other alternate explanations have not appeared that are as compelling, namely the unification of the forces, as well as the existence of dark matter and of the electroweak hierarchy, the hierarchy problem, which supersymmetry can help us resolve. So we have every reason to be optimistic that at this incredibly wonderful machine, which has proven to be so powerful at the hands of our experimental colleagues, and has completed this crucial test of the Standard Model, I think there's quite a reasonable chance that this machine can give us clues to discover how the forces unify. And as Hiroshi emphasized, how that might fit in, how we could fit that into a string framework. Not necessarily predict what kind of the phenomena that might be seen at the LHC, but at least incorporate whatever is discovered in a string framework. So here we can be quite optimistic. There are going to be experimental results in the next 20 years, lots of them. Some of them might give us real hints as to how the forces do unify and how that might fit into the string framework. The second question that I would like to be answered in my lifetime is perhaps a little harder, and that is, how did the universe begin and how will it end? Now, this is a slightly different kind of question, of course, and it's one that physics really hasn't ever faced before. But it's one that physics must face, since the universe, or the history of space-time, is a dynamical object whose beginning and whose end are subjects now of science. But it's extremely confusing. We don't really know what the observables are, nor what the rules are to answer such questions. And we are plagued by this cosmological constant, de Sitter space with all of its instabilities and problems of interpretation, and the specter of internal inflation, and the unmentionable principle. Now, perhaps we will get clues from CMB, from LIGO, or who knows what. But it is hard for me to see, unlike the LHC, that there's a reasonable chance of getting direct experimental information to answer that question: how did the universe begin and how will it end? My main hope here is that this is actually has to do with the difficulty of the question. This issue is a deep and very general conceptual problem of dynamical space-time, of quantum gravity. And as in the case of the black hole paradoxes, maybe, therefore, we can make progress. We've heard some discussion at this conference about the open conceptual issues regarding infalling observers into black holes, but to some extent, the deepest conceptual issues raised by the existence of black holes were answered by string theory, we believe, and even in the total absence of any experimental data on black holes. And so here too I can hope that perhaps there will be some help from observation. More likely this conceivably could be solved in my lifetime by thinking very hard about what is a very general conceptual problem in the dynamics of space and time. And finally, the third question I definitely would like to see answered is, what is string theory? And, you know, that question remains sort of open, even though, and the unbelievable progress that is made every year in the field only makes the question harder to answer. String theory, of course, started with the QCD string, before QCD. But that theory of extended stringy objects expanded rapidly to be a theory of quantum gravity, and now a theory of many other extended objects and of fields. And it has zillions of different formulations, It's not really a theory, of course, but a framework that seems to include everything that's nice and consistent in local gauge invariant relativistic quantum mechanics, includes strings and branes and all consistent field theories perhaps, and quantum gravity, and extremely hard to define. It has neither unifying principles or equations. Nevertheless, it has incredible applications, as we've heard, and we've seen wonderful examples at this conference, to QCD, to condensed matter physics, to mathematics, and hopefully soon to the unification. But what is it? Now, I've long felt that something is missing in string theory, and that one needs to answer this question to make progress. Of course, it might not. It might be that we first make progress and then understand what string theory is. That is often how things happen. But one of the ideas I always felt was missing was the understanding of string theory as an embodiment of some very deep underlying symmetry of nature, which goes way beyond the symmetries we know about. And there too, I think recent developments might give us hope that we're on the path, perhaps, to understanding better the symmetries, the underlying symmetries of string theory. Not that I have any idea what they are, but I think the newest and perhaps most exciting thing that I found at this conference and in recent developments are these higher spin symmetries that seem to be both dual to field theories and are some kind of baby version of string theory. Might be simpler than the full string theory analog, where one can make progress on understanding what the underlying symmetry is and how it's broken. String theory seems to have some underlying, seems to be some kind of manifestation of a broken, very unusual symmetry, but neither I or anyone else has been able to truly make any use of that or discover its structure for many decades. These Vasiliev-like higher spin symmetries are much simpler and might guide us, as some people in this conference have conjectured, to the underlying symmetries of string theory itself. So my general conclusion is that string theory is alive and healthy, and we're living in exciting times from both an experimental and a theoretical point of view. Anyone who's attended this conference is quite aware of the fact that string theory is alive and healthy. But there are two experimental observations I'd like to make that bolster this point. One is the point that was made by Hiroshi, which is that there are many new and brilliant string theorists. The one way of knowing, indeed, that's always a measure of the health of a field and the excitement of the ideas. And as Hiroshi stated, this conference was certainly a demonstration of the emergence of many new and brilliant young string theorists. The other observation is that the strings conferences as an institution continues to flourish. Now, this, I think, is the only major conference in the world that I know of that has existed for so long without a parent organization or anybody to foot the bill. In fact, no organization at all. Just every year, groups around the world volunteer to carry out this heroic task of running one of these conferences. I've always been concerned that it would die out, that one year we'd stand up here and say, well, does anybody want to run the conference next year? That hasn't happened. Every year for the last, depends how you count, but almost 20 years for sure, there have been groups of string theorists, around the world who have stood up and volunteered to run the conference. And as Hiroshi already said, next year our Korean friends are going to hold the strings conference in Korea, and then the following year our friends in the United States will hold the conference in Princeton, and the following year, it seems, our friends in India will hold a conference in Bangalore, and so on. This is a very healthy sign, and the only time we should start to worry about the health and vigor of string theory is when we can't announce the next 3 conferences at the end of these meetings. But at the moment, we're in Strings 2012, and I would like to end by giving thanks to all the heroic people who made this conference possible, including the International Committee, of course, but the local organizers, Ralph and Ilka and Gia and Johanna and Thomas, and especially Michael, who did, really worked very hard and made sure that all the talks would go smoothly. And Robert and Stefan and Peter and Slava, of course, Michael, Christian, Ivo, Stefan, and Martin. To the Silke, who arranged a wonderful coverage, I gather, in the press for this meeting, and for all the secretaries, Gabi, Rosita, Monica, Herta, and the many students who helped with a variety of tasks, but especially to Monica, who, I have it on very good authority, did most of the work. And last but not least, Dieter. To all of you, thanks.